Okay, I think that's mainly it. Thank you for joining us this morning for our video on CsCAN networking. The video is about 20 minutes thereabouts. As usual, if you have any questions, please enter them into your questions panel at any point throughout the video, and we'll get to them at the end. We'll get started there.
Welcome to today's tutorial. Let's get started. Today we're going to be covering CAN. We'll compare CAN and Ethernet, we'll talk about the CAN messaging structure and error detection, and then we'll talk about what CsCAN is and how CsCAN exchanges data. We'll discuss how I/O can be accessed over CsCAN with simple configuration, and as always, we'll finish with a live Q&A session. CAN, sometimes referred to as CAN bus, stands for Controller Area Network. It's a peer-to-peer communications network that allows microcontrollers and many other devices to communicate without a host computer. CAN is often used in harsh environments and is used extensively in vehicular and industrial applications. Let's compare CAN and Ethernet. CAN was designed for safe data exchange in harsh environments. When we say harsh environments, we're not just talking about cold temperatures and high humidity, we're also talking about very noisy environments from an electrical standpoint. Ethernet was designed to transport massive amounts of data in a reasonable time frame. It's since been extended to improve response times, make it more predictable, etc. Why are both CAN and Ethernet still in use? Billions of chips are sold annually that are supporting both CAN and Ethernet. The economies of scale for both are huge. Both technologies are used in applications where their individual strengths are more beneficial. Let's talk about the advantages of Ethernet and CAN. Ethernet can move huge amounts of data compared to other networks, for sure. Ethernet supports hundreds of common protocols, while CAN supports only about a dozen. CAN is a single-chip solution, which significantly reduces the amount of software and code required for communications. CAN has data integrity, which guarantees that no data frame is lost. Ethernet will discard incorrect data frames. CAN has a superior error recovery. It detects and recovers from an error 5 to 40 times faster than Ethernet can. CAN also has superior collision detection, as it arbitrates between multiple nodes without a message loss. Ethernet collisions result in lost messages and lost bandwidth. Let's discuss CAN messaging because it's very different from Ethernet. It's designed to move a relatively small amount of data very efficiently through harsh environments in a repetitive fashion. On the screen you're looking at the standard CAN frame. I'm not going to go through every element of that frame, but you can get the general idea. You have the starter frame, which starts everything off. You've got the ID, which is the identifier for the frame. A lower ID means higher priority. You've got the remote transmission request. You've also got the control data, which is there in the middle. Then we have the data that gets transmitted with the message. It's all wrapped up with a CRC redundancy check. You've got the acknowledged bit near the end, and then you have the end of frame, which marks the end of the CAN message. Now let's talk about error detection. There are 5 different ways in which it detects errors on the network. First, there's a CRC included as part of the message. That's a cyclic redundancy check, which is a 15-bit checksum. Then there's a form check at the message level. There are certain fields in the message that are a known constant value. If any of those fields are not that value, then the message is bad. Then we have the ACK at the message level. All nodes will listen to every message and will acknowledge valid messages. We have bit monitoring. As a node starts transmitting bit by bit over the network, it monitors each bit that is sent out to ensure it's correct. Then we have bit stuffing. This is a rule that states during a certain part of a message, you can't have more than 5 consecutive bits of the same polarity. When that happens, an opposing bit gets inserted into the message and is used as an error check. If it's not properly followed, then there's an error. Alright, now let's talk about arbitration. On the screen we've got a scope trace showing 3 CAN devices on a network. That's the bottom 3 traces. And then at the top is a trace showing the signal of the CAN bus in general. So what's happening is device B and C are both trying to communicate at the same time. Then a process called bitwise arbitration is used. When a device sends a bit out into the network, it will check to see if that bit comes back the way that it was transmitted. If two devices are trying to transmit at the same time over CAN, the node that's going to lose the arbitration sends out a bit that's going to come back wrong because that bit part of the ID was overwritten by the other node. Then the node that is losing arbitration stops transmitting but keeps listening. That means there are no bits lost and no bandwidth lost, and the message still goes through. Then the other nodes will monitor the message and acknowledge it if it's valid. This is useful in assigning priority to certain nodes. Now let's talk about CsCAN. CsCAN is a HORNER-specific protocol. It stands for Control Station CAN. It's very robust, in large part because it's built on the CAN chip, which is very robust itself. CAN was often used in a master-slave types configuration from a protocol standpoint. CAN isn't by nature master-slave, but a lot of protocols were created which used it in a master-slave type arrangement. Now at HORNER, we've primarily invented CsCAN protocol as a purely peer-to-peer network, which is much more efficient than master-slave protocols. We created CsCAN in response to a large-scale, high-speed material handling system. Existing networks weren't appropriate for that high-speed, wide-scale application. We've enhanced it over the years to make it easier to use, add I/O support, and that sort of thing. Let's discuss the functions of CsCAN. You can connect up to remote I/O. You can program multiple controllers over CsCAN. You can have multiple OCSs talking peer-to-peer, exchanging data safely and efficiently. The most common use of CsCAN is to add I/O to a typical OCS. We have what we call the single point of connect, or pass-through programming. That's a scenario where two OCS units are connected over CAN. With CAN, you have an ID that needs to be assigned to the OCS, and each OCS can have an ID between 1 and 253. We'll be using IDs 1 and 2, but the factory default is 253. We've got a computer connected over either USB or Ethernet, talking to OCS number 1. Through that connection, CsCAN can program both number 1 and number 2 by changing the target ID for the controller that it wants to talk to. Let's discuss how OCS to OCS communications work. We'll start by talking about global data. Each OCS that's on the CsCAN network can broadcast global data. Every node address on the network has 64 bits or 64 digital outputs that can be transmitted to the network through memory type QG. Each node address also has 32 analog outputs that can be broadcast as global data over the network through data type AQG. If an OCS needs to transmit more data than 64 bits or 32 words, you can assign multiple network IDs to it. So it could have a primary ID of number 11, but also have IDs 12 through 15. Then it would have 5 times as many bits and words that it can broadcast as global data. CsCAN takes advantage of the capabilities of CAN, and any OCS on the network can broadcast its global data anytime the bus is available using special Netpot instructions. Let's discuss how data is received. All OCS controllers have an area in RAM that's generally not accessible to the logic program. But there's an area in RAM where all the global data on the network is stored and updated automatically. As that data is broadcast over the network, the latest value for all the global data is automatically copied into this area of RAM. So every OCS sitting on the network has a copy of all the latest global data. There's a special Netget instruction that allows the global data in the RAM to be copied into local variables. That is how you receive data. Let's show you OCS to OCS Data Exchange, where we've got 3 OCSs sitting on a network. I've shown the RAM chip in each of these controllers where the global data ends up. Node 1 executes a Netpot instruction, which sends data to the network. The Netpot is executed, and now global data is broadcast by Node 1 to the network. The firmware running in Nodes 2 and 3 see the data on the network and automatically store it in their local RAM. And that works the same regardless of which node in the network is transmitting. Whether it's Node 2 executing a Netpot, sending the data to the network, and the other devices copying it into local memory, or whether it's Node 3 executing a Netpot, sending global data to the network, and the other devices copying it into their local RAM. Keep in mind, Netpots generate bandwidth. When you execute a Netpot, you are causing network traffic. To utilize global data from the other controllers, the OCS uses the Netget instruction. The local controller running the Netget instruction goes into its own memory, retrieves the data that's specified in the Netget, and copies it into a local variable where it can be accessed. Since a Netget really is just a copy instruction that accesses the internal memory of that particular OCS, it generates no traffic and uses no bandwidth, so it doesn't matter how often you execute a Netget in your program. Also, in a typical application, not all network data is necessarily relevant to each OCS. You only need to program in the Netget that you really need. It's entirely up to the application designer as to which data is relevant for each controller. Let's discuss some details about how CsCAN data is transmitted. The standard CAN message size is 8 bytes. They broadcast in groups, as per the table on the right. Now let's talk about bandwidth. At the default baud rate for CAN, which for CsCAN is 125K, your bandwidth is effectively 1000 messages per second. You can also use 250K, 500K, and even 1 MHz. Baud rate affects how long your network can be. Increasing your baud rate mainly affects your bandwidth, not your update rate. Now I'll discuss configuring CsCAN in CsCAPE. There's a CsCAN network configuration box that has important setup parameters for certain applications. Let's start with the network required checkbox. If you've got an application where you're using CsCAN at all, check it. It allows support of optimized mode, and network failures will turn off the OK LED. Next is the network optimized selection, which impacts how efficiently the data can be moved across the network. It should always be checked, unless you're servicing a product that's 20 years old. The next thing to configure is the number of network IDs. You can assign multiple IDs to a single controller here. The last one is the max packets per scan, which is important if you're utilizing CsCAN to move data throughout the network. It controls how many packets are sent per scan. Increasing the maximum packets can increase the bandwidth requirements for the controller. The Netpot instruction is used to generate messages on the network for either QGs or AQGs, and these do generate traffic, so you have to be careful that you're not overloading the network. The Netget instruction grabs data that's been received by the firmware and stuffed in RAM. That's where we retrieve it and stick it in a local variable. It does not generate traffic on the network. Let's discuss network heartbeats. If you're using peer-to-peer OCS communications, every OCS should be configured to generate a heartbeat. Periodically, the OCS sends out a heartbeat, which is a tiny message that lets the other nodes know that they're functioning. Then the getHeartbeat function block is used to make sure that other nodes on the network are sending you a heartbeat. If they aren't, communications have failed, and you can react appropriately with logic in your program. Now we'll do a live demonstration. I'll bring up a pair of OCSs on my desk here. We've got an EXL6 and an XL4. To keep things simple, I've pre-configured communications to go from the EXL6 to the network. Then the XL4 is checking the network through a netget function, retrieving the data being broadcast by the EXL6 and using it in its local program. The EXL6 is transmit only in this example, and the XL4 is receiving only. In a normal application, you'd have data going in both directions. Now let's open CsCAPE and have a look at how to configure this. Let's start in the EXL6, that is doing the broadcasting. This is the screen on my EXL6. All I've done here is configured a push button. I directly mapped it to the first global output bit, QG1. Okay, I didn't have to enter in an intervening M or T bit. I've also got a data field on my screen that is directly mapped to a global output, but this time it's mapped to AQG1, which is the word type global output. I have the ability here to change the status of QG1 and AQG1, which changes those values in the OCS itself. But that doesn't get the data out to the network. We get data out to the network through the Netpot instruction. Let's start with this first Netpot instruction, which is sending out the bit type data or the QG type data. The first thing the Netpot function block is asking for is an ID. I don't configure the ID of who will be receiving the data, I configure my own ID. I can either hard code that here, or I can type in the system register that contains my local ID. You may ask, why doesn't the OCS know what its ID is? Every OCS has the potential of taking up multiple consecutive CAN IDs. and I might want to be broadcasting this as ID number 1 or as number 2, etc. Next, we have to decide whether we're sending global data or directed data. We'll discuss directed data soon, but for now, we're sending global data. Now, are we sending out digital data? That's the QG type data, or are we sending out analog data? That's the AQG type data. In this case, we're using digital data, so that's QG1 through QG64 potentially. Where's the source data that I'm sending out? You don't have to type in QG1 here. You can use the data that gets sent out when it leaves the OCS. I've configured it for QG1 through QG16. The very first word of digital global data is what I'm sending. That's what will go out over the wire. You can think of this like a move command to a certain extent, and this particular source for the data could be anything you want. In this case, I directly mapped it here, QG1. Here's an important checkbox: send on change of state. It means when the data changes, the OCS will automatically execute this Netpot function block. If I didn't check that checkbox, every scan, I could be bombarding the network and using all of its bandwidth. With this checked, it only sends out data when it's changed. You have the option of choosing an additional variable, which will cause an additional transmission even if the data hasn't changed. I typed in M1 in my case. I could use the always off contact here if I didn't want an extra transmission. Number of words is down here, and you can only send them a word at a time. With this particular Netpot function, all 64 QGs fit within the same message, so even if you only send one word here, all 4 will get transmitted. I'm going to leave this at 1 because I may have other data that I want to map in separately. Okay, so this is the Netpot command for sending out my QG data. That's the push button I've got assigned. Right now, we also need to send out a separate Netpot for my analog data. I've only had that one data field on the screen. The ID is 1 this time, and I'll select analog data. It's the very first analog word I want to send out, so I'll leave my offset at 0. I've selected my source to be my AQG address. I chose change of state on this as well. If you don't want to send change of state, then you need to build some logic that detects when you want to send the data, and then executes this function block on something other than an always on. If you utilize the change of state feature, you don't need to build any logic. Okay, so these are the Netpot functions. Now when I execute this code, the EXL6 is getting data out to the network, but it's not getting the data in to the other side. We need to configure Netpots on the transmitting side and Netgets on the receiving side. Now to do that, I'm going to show you single point of connect. I'm talking over Ethernet to my EXL6, which is node 1, and my target is also node 1. However, when I switch it to the program from my XL4, it has a target of 2. So if you look in the lower right hand corner, I'm still talking through the same Ethernet IP address of the EXL6. I'm still physically connected to the EXL6 with a CAN node of 1. However, I am logically talking to number 2, which is my XL4. Let's go back to the screen here, and you can see the CAN cable that is connecting these two devices. I have Ethernet coming in here, and then I have CAN going out over here and ending up at the XL4. So that's called single point of connect. I'm now online with my XL4, and I'm looking at the program. We're seeing Netget functions. This is where you need to specify the node that you're receiving data from. Okay, so with a Netpot, you always use your own CAN address. With a Netget, use the CAN address of whoever is sending you the data. In this case, the data is coming in from number 1. Am I receiving the digital or QG data, or the analog or AQG data? Does it start at the beginning with an offset of 0, or does it start somewhere in the middle of the range with a higher offset? And then where I want to put it in my local memory. I'm putting in T1, which is an internal bit on this XL4 controller. I'm receiving in the first 16 bits starting at T1. The analog side is configured the same. Its analog is from the beginning. I have no offset, and I'm mapping it into R1. It's going into R1 because I'm only receiving one word here. To make sure everything's working like it's supposed to, I'm going to push the button. When I push the button on the EXL6, a Netpot is generated and it goes into the RAM of the XL4. The Netget function on the XL4 takes that data from RAM and copies it into the local program, where I'm displaying it on the screen. As I change it, you can see the response time is pretty fast. Similarly, with AQG data, I could change this to 85, and you can see the 85 showing up on the other side. Change this to 72, and it shows up on the other side as well. Okay, let's go back to the slides. How does CsCAN IO work? If all you want to do is add IO to an OCS, you go into the hardware configuration section of CsCAPE, add the IO, and assign it to the digital and analog input and output type references that you want to map it to. When it comes to CsCAN IO, you've several options. You've got Smart Rail, Smart Blocks, Smart Sticks. All those are different options for plug-and-play CsCAN IO. OCS controllers are powered from a 24-volt terminal block, and we have a standard 3-pin pinup. All CsCAN IO blocks get their power from the CAN network. Digital and analog inputs of an IO block are treated as global data, so when the data actually leaves the IO block, it looks like any other global data on the network. Digital IO is typically broadcast on a change of state basis. Analog IO is typically broadcast on a periodic basis. Analog and digital outputs work differently over CsCAN. They don't use global data, they use directed data. OCS is responsible for sending a CsCAN message to the output block to control digital and analog outputs. It's possible to have multiple OCSs monitoring multiple input blocks simultaneously, which means you can set up a warm standby type system where you have two OCSs that are controlling one set of IO over CsCAN. One is the primary, the other is the secondary. If the primary goes down, the secondary takes over without any kind of bump. But keep in mind, that's not an automatic function and has to be completely set up manually. Thank you for attending today's tutorial. The Q&A session will begin shortly.
Okay, that was that. Let's see if we have any questions on this. Is it possible to download the program for the 4E to the 6E and the 6E transmit to the 4E? I believe so, yes. I will verify this for you, but I believe so. Is there priority on nodes? Yes, if both transmitting at the same time, then the lowest node gets priority. Is there anything else coming in on that? Do we have a wiring sheet for the CsCAN? There will be a wiring diagram on your data sheet for wiring up CsCAN. So if you get your data sheet for your controller, you will find it there. Okay, that looks to be it for questions right now. I'll take you back to my screen and we'll show you what's coming up. So next week we have PID control, and then following that we have logic simulation, and then advanced math and function blocks. So these are at the usual time. So as again, every Thursday. All the registration links are here as always. If you haven't already, we'd appreciate it if you would sign up for these. It's great to see you there. And yeah, I think that's it for today. Thanks for joining us, and have a nice day.